Okay, so I posted your midterm grades. Class did very well overall. 87% was the median score. That's like, I was 27 questions out of 31. So there were 31 plus a bonus. Again, I don't, I'm not going to be returning the tests, and I don't let the students keep them. But you're more than welcome to come by during office hours to take a look. Right now, the midterms are just in this really big unorganized stack. So if you send me an email ahead of time, I can fish through it, and it'll be ready to go when you come to office hours. So just do that, and that's that. Any questions, concerns, or feedback before we go on? Okay. Well, we'll wrap up Chapter 5 today. Tomorrow's quiz covers Chapter 5, including some of the stuff I covered today. But I would say the majority of it will be the other Chapter 5 stuff, okay? But today's Chapter 5 stuff will be on there as well, okay? So maybe just kind of topics to know for the quiz. Topics from Chapter 5 to know. For the quiz, you know, so if I give you a kind of a table, right, and you got A and not A, and B and not B, okay, you should be able to answer all of the following, right? You should be able to answer probability of A, probability of not A, probability of B, probability of not B, probability of A and B, probability of A or B, probability of A given B, probability of B given A, are A and B independent, okay, and to check, how do we check if A and B are independent? You do probability of A versus, is probability of A equal to the probability of A given B, right? Because if they're independent, then the probability of A given B is just going to be the probability of A, okay? So you should know how to do all of this. You should also be able to kind of create a table on your own if given statements. So, if I give you statements, you should be able to make your own table. So just look back in your notes. I think there's an example about people who have cats and dogs and things like that, right? Okay. All right. I think that covers most of it. And then today's stuff, we're going to talk about kind of sequences of events and things like that. Okay? So plus. And they finally fired Byron Scott from the Lakers. I don't know if you guys care about this stuff, but all right, anyway. What? Oh, yes, absolutely. Too excited about stupid stuff. Let's see, what is this? Cancel. Okay. Oh man. Something's going on. Here we go. Are there any questions on this? I guess I'm just assuming we're okay here, but if there are questions here, I'm happy to take them as well. Okay, I guess we're good. All right. Okay, so we'll talk about kind of sequences of events. Okay. And these just kind of end up being and situations. Okay? So it could be something like you know, if there is a storm, so we'll do the storm at the airport, okay? If there is a storm, then the probability that a flight gets delayed will be 70%, okay? And then we'll say the forecast says there is a 40% chance of a storm. Okay? And so the question is, what is the probability that there will be a storm and the flight gets delayed? Okay? And so we can kind of diagram this out, and we can say, well, there could either be a storm or there could be no storm. And then if there is a storm, then the possibility is that there's delay or that there's no delay. Okay. So what's the probability that we end up going down the path for storm? 40%, right? Okay. And if we go down the path for storm, then what's the probability that we end up facing a delay? 70%, okay? And then so this branch over here for no delay will have to be 0.3, and this branch over here for no storm will have to be 0.6, okay? And so the answer to this question, what's the probability that there will be a storm and the flight gets delayed, is simply we just multiply these probabilities down the paths, and we get 0.4 times 0.7 is equal to 0.28. All right. The way we can, if I were to do all of this symbolically, I would say 0.4 is equal to the probability of a storm. Okay. And then 0.7 is the probability of, what would I write symbolically here? It would be, it's a given probability, right? A conditional one. So it's a probability of a delay given a storm. Okay. Is that okay? And so kind of the general form here, if we look at this, is that the probability of storm and delay, or I guess this would be, so storm and delay is equal to the probability of a storm times the probability of a delay given a storm. Okay. Or we would say probability of A and B is equal to the probability of A times the probability of B given A. Is that okay? All right, and this actually just comes kind of, it's a little bit of a circular reference. If I may flip to the next slide, it looks like some of you guys are still writing, so I'll wait. Okay, so if you recall, the definition for probability of A given, or would it, we're going to say B given A, is the probability of A and B divided by the probability of A. Okay, and if I just multiply both sides by the probability of A, then we get the exact relationship that we had on the previous page. Probability of A times B given A is equal to the probability of A and B. Okay? And so, these, the relationship will hold. And so sometimes, in some situations, you are given this information and you have to figure this out. Okay? And in other times, you are given these bits of information and you have to figure this out. Okay? And so, let's see if, here's a example. Okay, so we'll say if storm, then probability of delay is 0.7. Okay, and if no storm, then the probability of a delay is only 0.1. Okay? And then we'll say the probability of a storm is equal to 0.4. All right. So go ahead and kind of fill out your tree will look kind of will look very similar to how it was before. We've got storm versus no storm. Okay, and then see if you can figure out the total probability of just a delay. Okay, so what is the probability of a delay? Okay, and this is going to consist of two parts: probability of delay and a storm plus probability of a delay even without a storm. Okay, let's actually make a clicker question out of this. So let me think of some answer choices here. Okay. Okay, and see if I hope I I just did this in my head, so I'm hoping my answers are correct, but at least one of these are correct. Oh, you know what? No, one of my answer choices. Hang on a second. I got to. I apologize. Okay, and let me just make sure this is all correct. Stats 10 lecture 3. Okay, I'm hoping. So you'll want to fill out the little diagram. Okay. You can help out your neighbors if you wish. How are we doing? Looks like a lot of you guys are doing okay. All right, so we'll say 10 more seconds to get your clicks in. Okay, 3, 2, 1, and stop. Okay. All right, so let's label this out. So we can say, what's the probability that there's going to be a storm? That answer is 0.4, which means the probability that there is no storm is 0.6, okay? If there is a storm, the probability of a delay is 0.7, and no delay will be 0.3. And if there is no storm, then the probability of delay is only 0.1, whereas the probability of no delay will be 0.9, okay? So we want to know overall what's the probability of a delay. So we have to, there's basically two paths. We can experience a storm and then there's a delay, or even though there's no storm, we can still experience a delay, okay? And so if we multiply down these paths, we get the probability of a storm and a delay will be 0.28, that's 0.4 times 0.7. And then the probability that there is no storm and still a delay is going to be 0.06, so that's 0.6 times 0.1, okay? So this ends up being 0.28 plus 0.06, and I just want to make sure everyone's okay with that, so we get 0.34, answer choice E, and it looks like most of you guys got that correct, all right? And that there is our answer there, okay? So okay, so we have this relationship. Probability of A times the probability of B given A is equal to the probability of A and B, okay? So now I want to talk about what happens if A and B are independent, okay? If A and B are independent, okay. So we've got, so let's say A. So we have probability of A and B is equal. So this is kind of the general rule. Okay, so this is the general rule. Now, if A and B are independent, what happens to the probability of B given A? What is this equal to? Probability of B given A if A and B are independent. It's not 0. This just simplifies to the probability of B, right? Okay, because if A and B are independent, the probability of B occurring is not influenced by whether A has happened or not, okay? B is not influenced by A. Okay? And so when A and B are independent, probability of A and B simplifies to the probability of A times the probability of B. Okay, and so, and I think we're familiar with this relationship already. So we could say, if I flip a coin twice, what's the probability I get heads on both flips, right? Okay, and so this becomes, what is the probability that we get heads on the first and heads on the second? Heads on the first flip and heads on the second flip, okay? Which just becomes, because the first flip and the second flip are independent, this will become probability of heads on the first times the probability of heads on the second. Okay, because the first flip and the second flip are independent. All right, and so probability of getting heads on the first flip is just 0.5. Probability of getting heads on the second flip is also just 0.5. So the probability that we get heads on both flips is 0.25. Okay, and I think we have some intuition about this already, right? Okay, so let's just try a few of these types of problems out. Okay, and effectively, here, let me just throw in one more thing. Okay, so that's probability of A and B, and it can be expanded. So if A and B and C and D are all independent, A, B, C, and D are all independent of each other. This just becomes probability of A times the probability of B times the probability of C times the probability of D. Okay? And so on and so forth. Okay? All right, so let's try something out. Let's say we have a special coin. And the special coin will land heads with probability equal to 0.88. Okay? So we will flip 3 times. All right. I guess we'll do a clicker out of this. Let me come up with some fake numbers here. Okay, all right, so our answer choices will be So we'll flip the coin 3 times. What is the probability I get heads on the first 2 flips and tails on the 3rd flip? Now, maybe this question was too easy. All right, we'll say 10 more seconds here till, or I don't know, till it says 1:30. I'm gonna click stop at 1:30. 1 minute and 30 seconds. Okay, stop. All right, let's see. Okay, and that is indeed the correct answer. Okay, so basically we have to see the sequence. So the sequence must be heads, heads, and tails. And so that's going to be 0.8 times 0.8, and tails will be 0.2, right? And so when you multiply this out, you get 0.128. And there's our answer. Okay, notice, so this pertains just to an exact sequence of events. The answer here is different from if I said, what is the probability that I get 2 heads and 1 tails, okay? And this is something that will come in in the next chapter, okay? So you don't have to worry about this just at the moment, but, oops. Okay, so that answer is different, okay? So just, this is a note, and we will we'll explain all of this later, okay? So a note is that if I just ask, what is the probability I get 2 heads and 1 tail, okay, any order, then our answer, okay, our answer will be different. Okay, because this requires us to think of all possible orders that we can have, okay? We can have heads, heads, tails, which we established was going to be 0.8 times 0.8 times 0.2, 0.128. We could also have heads, tails, heads, and we can have tails, heads, heads, okay? The probabilities of these will be 0.8 times 0.2 times 0.8, and this will be 0.2 times 0.8 times 0.8, okay? Which, because of the commutative property of multiplication, all end up being 0.128, okay? But we would have to add all of these together. And we get something like 0.128 times 3, and I get 0.384. Okay, so you know, don't worry about this exact example for tomorrow's quiz, but it is something we will see again. Okay, and this is called binomial. So right now we're only just learning about kind of these exact sequence of events type of things. Okay, but it'll work out. Okay. So again, the distinction was that here I said any order is fine, whereas in the previous problem we had a specific order that we were concerned with. Okay, so let's continue on. All right, and so let's just try something out here. And so again, we have our special coin, where the probability of heads is equal to 0.8. Okay, and this one's going to be a little bit tougher. All right, we're going to flip it 3 times. Flip the coin 3 times. And here's the question: what is the probability? Well, let me make sure I get. Let me put my answer choices up first. Okay. All right. I got 0.2. Okay, so what is the probability I will get tails at least 1 time? Okay, so this is your question. So we're going to flip the coin 3 times, and we want to know what is the probability we get tails at least 1 time. Okay, so this, you can talk to your neighbors and discuss how you might approach this. I got clicks from about half of you. What was it? Okay, we'll say, I don't know, another 20 or 30 seconds. 30 seconds here. Huh? 30? I don't know. Well, I'll end it at 2 minutes and 45 seconds. All right, just 5 more seconds to get your clicks in. Okay, I'm gonna hit stop here. Oh, you guys did great. You guys did great. Okay. The answer choice. What? Are you guys? Okay, so let's talk about this. All right, so when you flip the coin 3 times, we can get different outcomes, right? And we want to get tails at least 1 time. So this means we want tails 1, 2, or 3 times, right? So we're happy if we get tails 1, 2, or 3 times. The only time, so we'll say happy if, and we will be sad if what? If tails happens 0 times, right? Are there any other possibilities? No. When you flip the coin 3 times, you're either going to get tails 0 times, or you get tails 1, 2, or 3 times. Those are the only possibilities. So these 2 things are complements to each other, okay? So these are complements. Okay. Now, we could go through the trouble of calculating tails 1 time, tails 2 times, or tails 3 times. It would actually be kind of tedious, but we could do it. But it's much easier to calculate what's the probability of getting tails 0 times and finding the complement of that. So what is the probability of tails 0 times? Okay. So then that means our sequence has to be what? It has to be heads, heads, heads. This means we got tails 0 times out of 3 coin flips. Okay? So the probability of getting heads on the first is 0.8, probability of heads on the second is 0.8, probability of heads on the third is 0.8. So the probability of tails 0 times is going to be 0.512. And the complement of that, which would be probability of tails at least 1 time, is going to be equal to 1 minus the probability of tails 0 times, which is 1 minus 0.512. And that gives our answer there, 0.488. Does this feel okay? Feel comfortable for you all? Okay. Well, great. So, as far as the probability stuff that you should know for tomorrow's quiz, I would say, know this example. Okay, of course, the numbers are going to be different. So you should know that the complement of at least 1 is 0 times, okay? All right, so we can do a few other examples that I think are kind of interesting, okay? But I'll say this will just be for your personal knowledge, and I will not be testing you on this, okay? But it is quite good, I think. Okay. So I'll just say star for your knowledge. Okay, and this is called Bayes' rule. Okay. So if we go back to our example about the flights and the delays, okay. So we'll just think back. There's a few things we could have done, okay? So if you think back to the flight and delay example, we said a few things. We said the probability of a delay given a storm was 0.7. we said the probability of delay given no storm was 0.1, and we said the probability of a storm was something like 0.4. Okay? And if we are given these pieces of information, we could, if we have this information, we can answer the question, probability of storm given delay, okay? What is the probability that there was a storm if the flight experienced a delay? Okay, and it might go about a little bit different from what you might expect, okay? And so I'm going to draw the exact same diagram that we had before. Okay. And we had something like this, 0.4, 0.6, 0.7, 0.3, 0.1, and 0.9, okay? So I'm hoping this is all okay with you guys from before, and we said when we multiply this out, we get 0.28. Over here, we get 0.06. So the total probability of a delay is 0.34. Okay, so far so good with everybody, I'm hoping? Okay, so here, we're asking what is the probability of a storm if the flight experienced a delay? So the question that we're going for is what is the probability of a storm given a delay, all right? So if I wanted to turn this kind of from the probability of A given B is equal to the probability of blah, 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 what do I put in the numerator and what do I have in the denominator? In the numerator, I would have the and version, and of these two events, right? It would be the probability of a storm and a delay divided by, and in the denominator I would put the probability of what? Of a delay, right? Okay, and so we would use this, and so in the numerator I would put 0.28, and in the denominator I would put 0.34. And I have 0.8235. Okay, so basically what this says is if the flight experienced a delay, the probability that there actually was a storm is now 82%. Okay, so okay, this is with this thing we actually get some kind of surprising results, and I want to show you an example where I think the results might be a little bit surprising. Okay. And we'll have just enough time to do it. Okay. All right. So let's say there is a rare disease. Okay, and so we'll say the probability of actually carrying the disease is 0.0001. Okay, so about 1 in 10,000 people might have this disease. Okay, and we'll say there is a test to detect the disease. And so we'll say if somebody has the disease, the probability, so the probability of correct detection, so the test result comes back positive. If you actually have the disease, we'll say that's 99%, okay? And then we'll say the probability of a false positive so this is probability of getting a positive result even if you have no disease is 0.01, okay? So 1% false positive rate. And then so the question is, you take the test, okay, you get tested, and the result is positive. What is the probability you actually have the disease? So this is probability of a disease given positive, okay? What do you guys think? On the order of 90%, 50%, 10%, 1%? What do you think is the closest answer? I think we haven't even done the, we'll say 99.9.5.1.01. Okay, which do you think is the closest, just from looking at this? This is just kind of a random one. So I will I'll write out the tree here. All right, just click something here. I'm not expecting you guys to get this one correct. Maybe we'll make it a. I think I can somehow make this a bonus question in the clicker thing. I think. All right, so just get your clicks. I'm going to hit stop here in a few seconds. Okay, so let me show you the answer. Okay, so we want the probability of, so if I multiply this out, I'm going to get 0.000099. Okay, and over here I'm going to get 0.009999. Okay, and so the total probability of testing positive will be these two numbers added together. Okay, so 0.123499 plus 0.121234. Okay, so I get something on the order of 0.010098. Okay, this is the probability of actually testing positive. What we want is the probability of having the disease given that we've tested positive. So that will be, on the numerator, I'm going to have the probability of disease and positive divided by the probability of testing positive. So on the denominator, I'm going to have 0.010098. In the numerator, I've got 0.000099. So I'm going to have 0.123499 divided by this quantity down here. Okay? And when you do that, you get something on the order of less than 1%, 0.0098. So the correct answer to this is 0.01, okay? You can, oops.
My clicker is that like the only way to get the